is the uh, which is the fastest hardware accelerator to be able to train this kind of deep learning models. And if you're interested and if you have seen the demos of Gemma has been trained on this kind of accelerators, pods of TPU V5s. And we're going to explore each of these kind of parts. Just write any question that you have in the chat. I will try to follow up, or the host will be able to stop me and tell me if you have any questions. And yeah, so let's start. So the first thing that we're going to talk is about JAX. So JAX being it's a proposed lightweight API for numerical computing, so arrays-based computing. What we want to have with JAX is to, over the last few years, people have been learning TensorFlow, PyTorch, even very old people were learning piano. And one of the things that we have found is that this put a lot of constraint on the developer. That being said, is that we expect people that are in numerical computing to actually learn a language to be able to express their ideas, and we think that it's not that the we should let the computers figure out which is the best way to accelerate our code, which is the best way to dispatch our code to hardware accelerator, which is the best code to differentiate part. And that's what JAX is going to be. And it's very, very similar to NumPy. So if you come from NumPy, you should find JAX extremely familiar. So apart from this lightweight API, we also have composable function transformations. So recall that in Python, functions are first citizens. That means that you can pass functions to other functions to generate other functions. And what JAX is going to provide you is going to be transformations that take functions, and then you can calculate the derivative of that function respect to any of the parameters. And this is what is called autodiff or auto differentiation. You can also just-in-time compile. That means that if you have a piece of code that you want to be fused, or you want to be like reduced to a very small number of operations to make your functions fast, you can just-in-time compile it. You can vectorize code. So if you decide that, hey, this function just works for this kind of images, then you can say, hey, what happens if I give 100, 200 images, and then it will create the code to actually vectorize your code. And finally, parallelization. So if you want to have a huge model in which you want to send the copies to different GPUs and each one of them to compute gradients, it can actually parallelize your code for you. I mean, this is the thing that it makes JAX so for me actually very interesting, is because now I don't have the pressure, nor I have to, hey, I carrying the batch in X dimension or carrying the parallelization in that dimension, but only JAX, I can just transform my functions using JAX. Also, this allows me to execute my code in both CPU, GPU, and TPU without changing any part of the code. The other cool thing that I really found fascinating about JAX is that it's extremely fast. So here we have the results of the MLPerf comparison. So what is happening here is that for each of the algorithms that we can find on a deep neural network. So here, the implementation of a ResNet, of a single shot detector, of a transformer, of a or a BERT model. If you write in JAX and you run on a TPU, you're going to find that it's extremely fast and very similar to other frameworks that you could have seen. So if you compare to TensorFlow, if you compare to MXNet, you can even compare it to PyTorch, and you're going to see that JAX, in the average, is one of the fastest frameworks that you can find at this for this part. So let us step a little bit back and let us consider, now that you have done a few classes on AI, is that how you actually might implement a performant and a scalable deep neural network. One of my favorite books is actually from a friend of mine who was a comedian before becoming a data scientist, is Joel Grus. He has a book that is called Data Science from Scratch. And one of his lessons that he talks about is that you should always try to learn subjects by doing like toy versions of it, right? So if you want to learn deep learning, I strongly suggest you that you do like a small model in which you implement the backpropagation algorithm, the multiplications, the activation functions, and we're going to see how we do it and my proposal. So here, if you already know NumPy, you're going to see that to implement to implement a multi-layer perceptron on an MLP, you can define a predict function that takes same parameters and input. We do some of dot products between those parameters, and we produce an activation function. Then we return this output. And the goal in deep learning is that to be able to learn WMB, the weights and biases. But this is something that I think that for every I'm going to add here one thing. It's very simple, in which this function is just the feed forward part of a deep learner. Apart from that, recall that for an AI system, we define an AI system something that we define a task, we define how good an agent is in that task, and the goal is to maximize how well that agent is doing into that task. For us, the task will be to reduce the MSE loss. MSE stands for the mean square error. So given W and B, you can set it arbitrarily. You can define, hey, this is my inputs. This is how they should look. I can just take the mean square error and figure out how it goes. So recall that for this, what we would love to is that we can take the gradient of the mean square error, that we can evaluate predict in a very fast way. And this is where Jax is going to Jax is where you're going to use, and it's going to be very, 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 very easy to find. So for this code, if we take a little step back, what we are missing is the following. What we are missing is that we should be able to run this on accelerated hardware. If you try to modify this code to be running a GPU or a TPU, you might need to have to adapt this to CUDA, adapt this to whatever TensorFlow, whatever PyTorch. You need, if you want to optimize this code, you might be need to do hand optimization via compile and fusion of operations. We want also to be able to, I don't know, if I define the mean square error, be able to take the gradient and compute the gradient on that part, and also that we can parallelize data and computation. And this is not something that NumPy can do, right? This is something that is very hard, and that's why we have this kind of tools of TensorFlow and PyTorch. But the proposal for JAX is that you don't need anything else. So let's see how JAX looks like. If you can see here on the left, I have the NumPy code. On the right, I have the JAX code, and take a look. So JAX also provides a namespace that is very similar to NumPy. So if you know NumPy, you can just change your code to jax.numpy.np. There are a few modifications that we need to do, which are related to accessors, but mostly I will argue that 90% of the NumPy code can be changed by using JAX, and you should have an improvement of speed. And when we are going to bring the transformation function, grad, which is be able to calculate the gradients of a functions that we define, bmap to vectorize the code, g to find optimization and to compile it so that it's fast, and pmat so we can parallelize our code. So we define exactly the same thing. Observe that the dot and the activation functions are similarly named. Oops. And then the mean square error also is we don't modify any of this part. So if I want to compute the gradient of the mean square error, I can just do grad of the mean square error. That will give me a function that will calculate the derivative of that function on that point. If I wanted to make it fast, I can just jit it. Yeah. If I want to do the gradients per example, if I want to per each, I want to have, I don't know, let's suppose that we have 15 examples. I want to calculate all at the same time. I can vectorize the gradient. So I take the gradient of the function, I can vectorize it, and I can make it fast, right? And if imagine that I have 15 GPUs connected to my computer. So what I can do is that I can calculate the gradient of function. I can pmap it. So each of the device will have a copy of my function, and each of them I can compile it in that card, and it will have a very accelerated function. So hopefully with this, we can see that one, we're able to run this code on the right, both in GPU, TPU, CPU, in any part of the code without modifying my code. I don't have to have the constraint that, hey, I want to send two device to CUDA of his CPU or everything. I can do it everything on the spot. I can do auto differentiation. I can calculate the differentiation without me remembering, hey, what are the rules for the derivatives? I can just program my code and the computer will be able to calculate the derivative. I can compile, so I can make it fast, and I can parallelize the code to any part. So take a look with only three to four new lines of code, we're able to scale this code. And this is the part that where Jax shines. So if you want to take anything of this of these few minutes of Jax, is that uh, Python Jax will transform your code into an intermediate representation that can be transformed. We're going to see a little bit how that happens in the next few slides. Uh, this intermediate representation enables domain-specific compilation. So the backend of all this kind of part that can run on the CPU, GPU, or everything is called is going to be XLA, which is extreme linear algebra. And these guys are focusing into that every single operation of linear algebra can be accelerated in any device, but you can work on the you can work on the work of them. So they will focus on to making this code fast, and you only think to provide is the code. Familiar user facing API. So both NumPy and SciPy are mirrored on the namespace of Jax. So if you have a code that you want to see if it's going to be accelerated, you can just change import numpy as np, or you can check for import jax.numpy as np, or import jax.scipy as scipy. And the powerful set of composable transformations. You can take the grad, you can JIT it, you can beam up, and you can beam up it. So hopefully you have the cool thing is that hopefully that will give you that you can use this as a black box, but I really encourage that people learn how to this kind of black boxes work. So let us see how this machinery works behind the curtains. The first question that I have for you is that what does this function do? So hopefully you have been been a Python developer for a while. It's clear for you that this takes something and then just add plus two. But the problem is that exactly what this does function do is that before we do, if we don't know x, this function can do anything. For example, I can define an object called an expresso maker that is an object, and I can overload the plus operator. So whenever a plus operator happens, I can open an SSH version to any computer. And if I call F to that, it's going to create an SSH connection. And this is, imagine you define something that you expect to be in like in the mathematical realm, and then finally the object is just trying to do like an SSH connection to that. And this is something that is due to the Python dynamism. So due to Python be very dynamic, a function can do anything a function can do anything depending on its input. So that's why Python is slow compared to Go, comparing to Rust, to any of the compile language, because before you are executing or you are interpreting your code, this function can do can do anything. So same as life advices, you take problems and you convert it into opportunities. So what it's going to Jax do is that thanks to the dynamics of Python, we're going to change our x and we're going to define it to be a tracer value. And we're going to trace what happens during the call of the function, and that will generate the intermediate representation that I was talking a few slides back. So for example, instead of defining an expresso maker machine object, I can define a shared array, and that every time that's happening, if there is a computation of add, plus, change site, or do a convolution, I can just record that computation that's going to be in my object. And then finally, I can check if it changed of D type, if it changed shape. And then I will call my function to that part. So whenever I go through the first time, I will be able to trace what the function do to my inputs. So let us see a specific example that in here. So here we have import or JAX, and these slacks are the one-to-one mapping of the operations that happen on Python to the XLA backend. So you have like you are really working with the most efficient version of it. We define a function that calculates the log of two of a number, and we define this operation. As soon as you create an array and you JIT it to this part, we're going to create the intermediate representation of it. So you define your function, you define, so first you calculate the log of that number and you set it on B, then the C is going to calculate the log of 2, and then finally is the division. And after you pass your trace value, this is the intermediate representation that is going to happen. And what the JAX backend is going to do is that with this intermediate representation that is called a JAX expression, you will be able to take the gradient. You're going to be able to vectorize this function and to get it, because now you know exactly what is happening to the function, what exactly you need to vectorize if you want to add a batch dimension, and what exactly is going to need to be, because look, if I do the log2 log a, if I have the JAX expression, I can just fuse the two operations with the hardware backend equivalence of it. So it makes extremely fast, and you're going to see a lot of JAX expressions whenever you are doing you want to see what is happening in the backend of JAX. This machinery or this backend, you don't need to go to the very specific details to be used. It's part of a huge ecosystem that allows you to do high performance computing. So you can do JAX tracing, and it's going to give you the JAX expression, which is a subset that is a language that is subset that is a small untyped. As soon as you read it, it's going to create an HLO operation. This is called a high level optimized code. And from the high level optimized code, this is going to be both to the XLA, and the XLA will manage the code that goes to the TPU, to the GPU, or to even to your same computers. And the user has control to say, hey, I want this to be fast. I want B to this dispatch to this accelerator. I want this to be vectorized. Yeah. And the whole thing is that none at this point you have to consider where your code is going to run. It's just you are free. You are free from the constraints that the code should focus into the hardware. There are many things to do. So in my work, so robots that do segmentation use JAX on it. Embedded devices that have JSONs between them. Most of the diffusion models that you can see on the web that in which we generate images and everything are used JAX in this part. Machines that can do separation of trash. So hopefully this will give you an interest to be able to learn JAX. Now, the problem with JAX is that it's very low. It's very low level. Sometimes you don't want to see what is the XLA operations. You want to have something like a much more to a TensorFlow or a PyTorch model. So this is where flags come in. So assuming that JAX, you have your building blocks, we're going to use deep learning. We're going to use deep learning via the use of flags. So Flags, it's a Python install library, also developed by Google DeepMind. And the properties of this is that it's a Pythonic library, intuitive, predictable, explicit. It is very simple. You're going to see how we can call these models very fast. And one second. And it integrates years of user feedback of being able to TensorFlow 1 and TensorFlow 2 for the developers. So how does a Flags model looks like? So on the left, we have the JAX implementation, in which you define a setup, you define a linear model, then you block, and this will throw you an error. Uh, what we want to do in NNX is that as soon as you define an init, these models are really, really already available for you. The only thing that I will not explain that will be part of something that I want you guys to look is that the generation of random numbers, since JAX is very functional, is a functional framework. Uh, you want to be able to have control of how random numbers are propagated to your models. So this is going to be part on this link if you're interested, but just whenever you see RNGs, just keep it as a black box that generates black numbers. I will not explain this today. But as soon as you display, you're going to see that this block will be able to show you, hey, this is a model linear that has the following models. That is a bias, how was initiated. So if you're using a different initialization, such as zeros, such as hey initialization, what is the operation in lags that is doing the backend computation for this model, and the parameters. If you're doing like the kernel, you're going to see that you'll be able to see like the values of the kernel, and if it has a bias, also the values of the bias. So now we're going to jump to a full demo. Um, Sorry, one sec. I'm going to share my other screen. Just one sec. So now we're going to use Flax directly. The cool thing is that we can do it on Colab, and we're going to restart the session. We're going to take a GPU part. Yeah. Runtime, run all. So Flax was released a few weeks back, so you will need to have the 0.84 version. You are going to see this part in a minute. What we're going to solve, or what we're going to solve in this full example, is to the CFAR10 library. So the CFAR10 is just a collection of images of 32 by 32 by 32 by 32 uh, rows and column. These are RGB images that we want to classify into 10 categories. We can use the TensorFlow dataset to have our loaders, right? I calculated outside of this class. I calculated the standard deviation and the mean of this data set. So these are going to be the values in which we are going to normalize. Recall that for machine learning algorithms, it's always very an excellent practice to keep always to normalize our inputs, divide by the standard to rest to subtract the mean and to divide by standard deviations. So our inputs are normalized to a normal distribution. We're going to train for 6 epochs, and we're going to do by batches of 32. So as again, we normalize examples. We have container or labels. This kind of operation that the number of parallel calls, we're going to let TensorFlow handle automatically the production of files. And the same thing we're going to do to our test dataset. Okay. Now, how does a model in Flax looks like? So in the init, you're going to define all the models that you need. So here, as you can see, NNX also provides the layers, such as a convolutional that we take so images of that has 3 channels to generate images that have 32 channels. These are going to the parameters that we're going to read. Also, we define a second convolution that takes 32 images that have 32 channels, and then we generate images that have 64. Finally, we define an average pool model that is just the same average pool that is on NNX that has, and we're going to hard code the window shape and the strides. We're going to define also 2 linear models, one that takes 49 vectors 4096 entries and goes to 256 entries, and from 256 entries we go to 10. And in the code, we're going to see how these models are connected. So first, we're going to do the convolution on the images that have 3 channels. Then we're going to do a ReLU activation, an activation function. Then we do an average pool. From this, we do the second convolution. We call an activation function, and then our average pooling. Then we just flatten our images, and then we run both the linear one and the linear two. So we end up with a vector of 10, and this is how it looks like. So the cool thing is that Flax provides this awesome display that will allow you to calculate to see how the parameters of each model. So here are our convolution one, convolution two, which are which parameters are the kernel and the bias. So the bias is going to be here, and the kernel is going to be here. So the kernels are 3 of the shape 333 with the standard deviation of this, with the mean of that, and yeah, and the bias. We're going to be able to see that the models that are linear and linear 2 are there also. Yeah. So if we call JAX on the numpy array, oops, is here. So we create a function that has, this is going to be our batch, the images by 32 by 3, and we apply this function to that. We're going to see that our vector, let me see if we can do it a little bit larger. JAX NNX is also going to provide us with the values at the of the last layer. So these are going to be our logit for the models when we calculate the softmax and cross entropy, right? Optax is the library that joins JAX to do optimization. So if we want to avoid us to program the Adam optimizer or any kind of optimizer, we can use NNX. Recall that Adam just has one hyperparameter, which is the learning rate. We're going to start with a very small one. Then we give our model, and then we say which metric we are going to follow. And observe that also the Optax modes are JAX modes, so we can see which are the state of the optimizer, how does it look like, the values, which are the models that are being tracked by the optimizer state, and which is the status at this moment. So I have a need and an update function. Now we're going to define a function that has a signature that receives a model and receives the batch images. We get our logic of calling the model on the batches, and then we call, hey, how good or how bad it goes. Optax has also the loss functions already implemented. We call the softmax cross entropy with integer labels. We give the logits and the batch, and then we return how good and the loss and the logit. Now the train step is just we call from NNX the value and grad part. So the value and grad is also a JAX transformation that you allows you to gather to have the function that calculates the value, and at the same time also the function that is the gradient at that step. So when we call this is a function. The grad function will give us both the loss and the logic, which are here, and in the other side is going to give you our gradients. Now with the gradients, we optimize our metrics. So knowing which was the value of the loss, what was the logic, we define what was when where was evaluated, and then we just optimize the update with the gradients that we have. And it's just a matter of passing functions and values. Finally, our evaluation step. Also, I forgot the correct of JIT. So this is going to be evaluated once, and as soon as it was evaluated once, we're going to have a just-in-time completion of this, which will make the code very fast. And we define finally our train methods. So we iterate over our train data set. We define that if how many files there were there, and then how many epochs that we want to have. So we just iterate on those. And the only thing that I want you guys to focus is going to be on the train step, right? So the model optimizes on the metrics. You just pass which was a model, which was our optimizer, which was our metric, and finally just go to track the loss, and so we can print the logs and the values. Take a look that for a T4 we take 15 seconds to pass an epoch, 9:27 to pass an epoch, and as soon this stabilizes around 9 seconds. I'm not going to run the code without the CPU. I'm just going to have you the results that we have in here. And take a look. So on the top, we have the CPU values. So for CPU, it took us 160 seconds to pass over an epoch using JAX. And on the down, we have our T-force, which was 9.60 seconds to pass another. So we have a huge improvement on the speed, and look that the code is exactly the same. I never had to specify, hey, just be careful, this for CPU, hey, model.device, that doesn't exist in JAX. It's just, I'm just using the XLA backend to find that. So I mentioned at the start of this talk that we were going to talk about TPU. Colab has a TPU, but it's a very old TPU that is not like, it's mostly on the deprecated side. So we're not going to use the Colab TPU in there. But for those that do not know, that this is a TPU is a hardware specialized to compute deep learning matrix multiplication developed by Google. It's internally at Google. There is no commercially available product that you can buy. And this is one of the TPU before pods. Just to let you know, this is one of the few pictures I could gather, and probably Gemini or BERT at the epoch was trained on one of these pods. So each one of these small machines has it's imagine like it's a twice or five a GPU, and this pod's probably 123 teraflops per operations. And yeah, so it hits 1.1 petabytes of seconds when you need to do already. So these are extremely specialized machines that can do very, very fast calculations. So if you want to know the details, mostly what you can do it is, what you can see is that it works the same as the heart. So the heart has a systolic mechanism. The same thing is going to be the crux of the TPU. We're going to see the images can be separated into patches, and then each one of them is passed to a matrix multiplication unit, and the accumulator and everything is going to be it's going to be at the end on a high bandwidth memory, and then you just recollect the results. So this will allow you. This is the hardware that allows you to train very extremely large models. So where you can get a TPU, the only way that you can get it is through the use of Vertex AI on GCP. So you can see what we're going to focus only is only in the part of pipelines. But Vertex AI is a very, very complete framework of Google that allows you to have machines to train deep learning neural networks. And the way that we're going to use it is through the use of Vertex AI pipelines. So Vertex AI pipelines combines the use of Docker and Kubeflow. So you define like a direct acyclic graph in which each of these models, each of these nodes is a container component. And you decide, hey, for this component, I want to use a TPU or a CPU. So how a code in Kubeflow looks like, you define a container component. So this is going to be the part that you need to learn Docker to be able to use Kubeflow and Vertex AI pipelines. You define a component. So for example, here is my TPU example that is on a TPU. Here is my code, which is exactly the same code that I download from the Colab. I just took file download, I put it into a container, then I define my component. I want to have this kind of machine. The CT5LP is going to give me a TPU. The accelerator type is a TPU v5. I just want one machine and has 150 gigabytes. Then I define the pipeline that calls these components. So I can just call the custom training job, in which project. The locations, TPUs are mostly on the US West and US West, and one in Europe. I don't recall right now which was the region. And what is cool is that this component just calls the container, and we're going to see that it takes only 7 seconds to cross over the epoch that we did with the CFAR example. So we started from 150 seconds from CPU to 7 seconds in a TPU. You can optimize even more. I don't think that we are using the full power of the TPU, because mostly of our models were very small convolutions, so we are not even use all the pod that is available. But as soon as you start to see to add very large models, you're going to see that this gap between CPU and TPU is going to be extremely huge, probably of the order of 100x or 1000x. So yeah, this is a work that we have been doing a lot in our consultancy. I will put things that have gone wrong with the presentation. So TPUs are very difficult to gather. Sometimes in GCP, you're going to see that the resource already exhausted, that you cannot get any more TPUs for days. So I was able to do this with the support of Google. I'm a technical coach for people that are machine learning engineers and just want to scale up their career. So if you want to add me, here's my LinkedIn if you want to add me in there. And yeah, so I'm here for questions, and hopefully that wasn't that. Hopefully, you guys could have learned JAX, NNX, and see what the TPU does. So I think that will be for me. I'll be here open to questions, that to any observations. So just let me know.
So, thank you for being here today. We
Mhm.
appreciate your time and engagement throughout the session. So, first and foremost, I would like to extend a heartfelt thank you to our esteemed speaker, Mr. David Cardozo. Your insightful presentation was incredibly enlightening and has provided us with valuable knowledge and perspectives. So, the key takeaways will undoubtedly benefit us in our respective roles and initiatives. So, personally, I found the discussion on this topic particularly fascinating. So before we conclude, does anyone have final questions or comments to our speaker?
For sure, I will put
So
the.
please proceed.
Oh, yeah, I see a few questions on the messages. I will put the work. I will put the slide deck. I will send that to Bill to sorry to the AI camp part, so you can ask them as soon as the presentation. I will just create a link for the both for the workbook and for the slides. So yeah, I think that will be for me. Thank you very much, and hopefully, hopefully I have put a little bit of curiosity you guys to learn. High scientific computation, and yeah, just let me know if I can be of any help. All right.
Okay, thank you, David. So I had a
So
question
we
like
value
this.
your feedback to help us improve our future sessions. Please take a moment to scan the QR on your screen and fill out a brief feedback form.
Yeah, Dirash, you had a question.
Actually, so I had a question regarding that. The
Mhm.
the framework is just to for accelerating the training process on the GPU.
Mhm.
It cannot do anything on the CPU side.
Any operation you can do it on CPU, just it will take you a long time. So imagine that you want to do where you I mean convolutions, you cannot do it really fast on a CPU because you are limited by the number of cores. And if you have like imagine 60 cores compared to like the 1,000 that you have on a GPU, but what you can do is just emulate a convolution on CPU. It will only take time. There are a few new computers that are doing like I know that Intel and AMD are putting hardware register to compute convolutions inside of the processor. So what I hope or what is going to happen in the future is that maybe XLA will actually map those hardware accelerators in the through the use of XLA. So they're going to map that. But the thing is that you shouldn't care about that because those guys of the XLA would just provide you the backend to do that. So all the acceleration could also eventually you will have a code that with the new processors you can actually see an optimization on the CPU. But the optimization can be done on any platform. Jax will always try to give you the best code that you have depending on the hardware that you had at that moment. So yeah, you will see. I'll say that you'll see a little bit of optimization, not as much as using a GPU or a TPU, but you'll have an optimization.
Okay, thank you.
With all the pleasure. All right. So if that's for me, thank you very much, guys, for being
There
here.
are, excuse me, there are several questions in the chat, if you don't mind addressing those.
Yeah, for sure. Just show me, point me the way, please.
So the first question is, are you going to share the workbook, the
Yeah,
notebook?
yeah. I'm sending
Okay.
this to Bill in a few minutes,
The,
and then yeah, you guys can
the,
take it from there.
there is another question about either PyTorch, TensorFlow, or JAX Flags. Which one to use?
So this is the part in which I think that I'm going to say the same answer of which language program to use. All of them looks at the same, like PyTorch and TensorFlow. As soon as you start to do deep learning, you're going to see that they have similar API. The cool thing about JAX is that you technically don't need to learn JAX because as soon as you know NumPy, you already know JAX, and that's what I wanted to express in the few slides. So uh, for where to use production things, I think you should use whatever is battle tested. So I will argue TensorFlow and PyTorch. But as soon as you have, like if you're doing a research project and you want to be able not to think about how to make this fast and everything, just use JAX. And yeah, the future is going to be well. I am by no means I can see into the future, but I do hope that most of the research code than laboratories and laboratory that laboratories and industry is going to use JAX. So I think if you're doing something that is critical heavy, just use the old frameworks. If you're doing something that you want to just to do a proof of concept, just use JAX.
Thank you.
With all the pleasure. All right, if that's it is, yeah. So see you guys. Have a good afternoon, and yeah, thanks for being here. Bye bye.
Thank you, David.
So thank you once again for sharing your expertise with us today. So additionally, we are excited to announce the upcoming Next Gen AI Camp on July 1st, where you can master foundational concepts using Gen AI and cultivate daily practices to enhance your skills. We encourage everyone to participate in this enriching opportunity. Thank you.